Welcome back to Linear Algebra. I'm Dr. Jeff Groh. Today we're going to look at linear combinations and linear independence in the context of finite dimensional real vector spaces. This is kind of a warm-up problem. For the more advanced theory that we're going to be discussing later in the course. We're going to start with a set called R2. It's more than just a set. It is a collection of points. It's a collection of points where we have two coordinates, x1 and x2. We are going to look at these as column vectors, such that x1 and x2 are elements of the set of real numbers. We're going to impose on this set two operations. First of all, vector addition. What do we mean by AB plus XY? It is, by definition, A plus X, B plus Y. You add corresponding coordinates. Also, we're going to define what we mean by A times XY. That is defined to be AX, AY. What do we mean to say that two vectors are equal? We say that AB and XY are equal if A equals X and equals Y. In this case, we write AB equals XY. Go figure. The definitions that we've given so far can be extended to Rn. In Rn, the vectors will look like x1, x2 through xn, and addition and scalar multiplication will be defined in the obvious ways, as will equality between vectors. We're going to explore properties that are in common to each of these vector spaces. One of those properties is the commutative law of addition. We know by the definition of addition that AB plus XY is A plus X, B plus Y. These coordinates represent additions of real numbers for which we know the commutative law holds. So A plus X is the same as X plus A, and B plus Y is the same as Y plus B. But then we may deduce that the vector X plus A, Y plus B is the vectors XY plus AB. We see then that addition can be reversed. This follows because of the commutative law of addition for real numbers. We have the following theorem. If U and V, the theorem will go in the same way for each of the Rn's. If U and V are in Rn, then U plus V will give the same result as V plus U. This is called the commutative law of addition. In each of these spaces Rn, there's a special vector which we'll denote by 0 with a little arrow over the top. It has all coordinates equal to 0. Clearly, if you add 0 to some other vector, it leaves it alone. So if I have 0, 0, and I'm adding that to 2, negative 1, I get 2, negative 1. It's not the same thing as the symbol 0 by itself. It's different because it has a number of different coordinates, all equal to 0. For vectors, when you add the 0 vector to another vector, you just get that other vector. So it behaves just like 0 should, but it's not the same thing. Every vector in Rn also has an additive inverse. If you take a vector u and add it to its additive inverse, you get the 0 vector. In fact, this defines what we mean by additive inverse. For every vector a, b in R2, its additive inverse is the vector negative a, negative b. Also note that if I take negative 1 times u, I get negative a, negative b, which is the additive inverse. Do you see the subtle distinction that I'm making between minus u and negative 1 times u? I'm trying to get at the idea the additive inverse may or may not be negative 1 times u. We'll show that for all vectors Rn that this will be true. In fact, there's a compendium of properties that Rn has. Let u, v, and w be elements of Rn, and let a and b be elements of R. Then we have the following 10 properties. I like to enumerate it as 10 properties because I want to emphasize certain facts. First, we have the closure law of addition. This is so obvious that some texts don't include it. However, I like to emphasize this property so that you have it in mind. When you add two elements of Rn, you get something in Rn. That's called the closure law. You can't take two things in this vector space Rn and add them together and get something that's not in Rn. The set is algebraically closed under addition. Second, it's very unusual for a property like an addition to not have the following property. It is associative. There are operations that are not associative. For instance, the cross product, way back in pre-calculus, that's not associative. So it's pretty strange. It goes like this. When you add u plus v and then add w, you'll get the same thing if you add u and then v plus w. We've already proved property 3, the commutative law of addition. Property 4 is the property of 0. If you set 0 to be the vector with all coordinates equal to 0, then 0 plus u gives you the same thing as u plus 0, and that gives you u. Property 5 is the property of additive inverses, negatives. you set u equal to -1 times u. Then u plus its additive inverse is the same thing as the additive inverse plus u, and that is the zero vector. That ends the purely additive properties. Now we begin the multiplicative properties and the properties that mix both multiplication and addition. First, there's a closure law of scalar multiplication. When you take a times a vector, you get a vector. As with every good operation, there's an associative law. Not that the cross product isn't a good operation. If you take a times b times u, you'll get the same thing if you take a times b and then multiply onto u. In property 8, we have the property of 1. If you rescale a vector by 1, it leaves it alone. All of these properties are not all that complicated. They're pretty simple. We're just teaching you the names. There is distributive property number 1. It goes like this. If you take a scalar and multiply by the sum of two vectors, you can distribute that scalar factor to each term in the sum. I did say there would be 10 properties. This is the last one. Distributive property number 2. If you have a plus b times u, then you can distribute the vector across the scalar sum and have a times u plus b times u. These 10 vector space properties will be generalized to more abstract vector spaces later in the course. For now, I'd like to note in a theorem that if you take 0 times a vector u, you get the 0 vector. And the proof is pretty obvious. If I take 0 times x1 through xn, I get 0 times x1 through 0 times xn. Each of those is equal to 0, and that gives me the 0 vector. What is important to keep in mind here is the difference between 0 without the half arrow over the top and 0 with the half arrow over the top. There's a unique role for certain vectors in Rn. For example, consider E1, which R2 is the vector 1, 0, and E2, which is the vector 0, 1. These are special. Sometimes they're called I and J. And every vector in R2 can be written in terms of these two. If we have xy, we can rewrite that as x0 plus 0y, and then as x times 1, 0 plus y times 0, 1. It seems that these two special directions can be used to construct every vector in R2. We call this set the standard ordered basis for R2. This decomposition of vectors in R2 as x times E1 plus y times E2 gives you a sort of city map direction on how to get from the origin to these points. You'll go x units one way, and then y units another way. So it's like saying, go west, x blocks, and then go north, y blocks. We're going to make a definition. The standard ordered basis for Rn is E1, which has coordinates 1, 0, and then 0. E2, which has a 1 in the second coordinate and then all zeros, through En, which looks like zeros until the last coordinate, which is 1. This is called the standard ordered basis, or the SOB for Rn. Yes, this is the standard abbreviation for standard ordered basis. Notice that in R2, the SOB consists of 1, 0, 0, 1. In R3, the SOB consists of 1, 0, 0, 0, 1, 0, and 0, 0, 1. We're not saying this yet, but consider, R2, is that two-dimensional space? It's the plane. And it has two elements in its standard ordered basis. R3 describes points in space, 3 dimensions. We have 3 elements in the standard ordered basis. Do you think that's a coincidence? We're going to explore that in more depth later. For now, it's sufficient to note that any vector xy in R2 can be expressed as a scalar x times 1, 0 plus a scalar y times 0, 1. Expressions of the form on the right-hand side are special, and we're going to give them a name. Let S be any subset of Rn. This set S could be finite, but it could be infinite as well. Any finite sum of the form C1 x1 plus C2 x2 to Cn, I'll say m, xm. I don't want to confuse this number with the dimension of the space that we're in, where x1 through xm are in S, and C1 through Cm are just scalars, real numbers, is called a linear combination of elements of the set S. So linear combinations are very simple kinds of sums. It's a scalar times vector plus scalar times vector and so on. But it's finite. It can't be an infinite sum. Infinite sums require the additional concept of a limit. So we're not going to add that on yet. Linear combinations must be finite sums of this form. So for example, if our set S is 1, 0, 0, 1, then any combination of the following form, C1 times 1, 0 plus C2 times 0, 1, is a linear combination of elements of S. Note that after you form this linear combination, you get something that may not be in the set S. It could be outside of that set, and that's okay. In our next example, we're going to look at the set S, which consists of the vectors 1, 0, 1, 0, 3, 3, and 1, 2, 3. We'll ask, can we write 0, 0, 1 as a linear combination of elements of S? This is equivalent to asking, do there exist constants C1, C2, and C3 such that C1 times 1, 0, 1 plus C2 times 0, 3, 3 plus C3 times 1, 2, 3 equals 0, 0, 1. I want you to see something. This answer to this question is the same as the answer to the question, is there a solution to the matrix equation (1, 0, 1, 0, 3, 2, 1, 3, 3 all times C1, C2, C3 equals 0, 0, 1. You can see this because if I add this up on the left, I'll have C1 plus C3, 0, I'll have 3 times C2 plus 2 times C3, and then C1 plus 3 times C2 plus 3 times C3. All of that equal to 0, 0, 0, 1. This gives me a system of equations. So determining whether or not some vector can be expressed as a linear combination of a given set of vectors is equivalent to, is there a solution to a system of equations? We know how to answer the question about the existence of a solution to a system of equations. We can just set this up by putting these vectors into columns of an augmented array. Perform a sequence of elementary row operations, and then answer the question, do the constants C1, C2, C3 exist? In other words, is the system of equations consistent? Let's check it out. Let's take -1 times row 1 and add to row 3. That gives us 1, 0, 1, 0, 0, 3, 2, 0. Then we'll have 0, 3, 2, and then 1. Now we'll take negative row 2 plus row 3, and that will yield a new row 3. That leaves the first two rows alone. And we'll have 0, 0, 0, and then 1. The last row is a contradiction because it expresses the equation 0 equals 1. We deduce that this system is inconsistent. That means then that the vector 0, 0, 1 cannot be expressed as a linear combination of the three vectors that we gave originally. Our answer will be that 0, 0, 1 cannot be expressed as a linear combination of the vectors in the set 1, 0, 1, 0, 3, 3, 1, 2, 3. Don't get cheap with me. Write out the whole thing. When it comes to solving problems in this course, it's better if you write things out as complete sentences as best you can. That way, you can go back and read what you've written. I suggest the following strategy. When writing out homework problems, write out the question in complete form, and then write out a complete answer. That way, when you go back to study your homework, you'll be able to understand what you've written. I learned this the hard way in graduate school. Writing out gibberish that is all in fragmented form, not in complete sentences, is worthless. As another example, we'll ask, can 0, 0, 1 be written as a linear combination of vectors in S equals 1, 0, 1, 0, 3, 3, and 1, 2, 4. Let's find out. We'll put things into an augmented array again, just as we did last time. And perform a sequence of elementary row operations to obtain the reduced row echelon form. My calculator gives me 1, 0, 0, minus 1. 0, 1, 0, minus 2/3. 0, 0, 1, 1. We can see now exactly how to perform the linear combination. The constants are going to be C1 equals -1, C2 equals minus 2/3, and C3 equals 1. Let's see that in practice. Let's take -1 times 1, 0, 1, minus 2/3 times 0, 3, 3, and then 1 times 1, 2, 4, and see what we get. We get -1 and 0 and 1, that's 0. 0 and -2 and then 2, that's also 0. -1 and -2 is -3 plus 4 gives 1. We can see that there is in fact a linear combination of these three vectors that gives us the vector 0, 0, 1. To find the coefficients, all we had to do was solve a system of equations. Maybe you can see why we spent so much time solving systems of equations. You'll see a lot more of this. For now, I want to make a special note. Every vector x1 through xn that lives in Rn may be expressed as a linear combination x1 times 1, 0, 0, x2 times 0, 1, 0, 0, and xn times zeros and then 1. That means that every vector in Rn can be expressed as a linear combination of elements of the standard ordered basis. I want to show that x squared plus 2x plus 3 is expressible as a linear combination of the elements of the set 1 plus x squared, 1 minus x squared, and 1 plus x. You can see that because if I take c1 times 1 plus x squared plus c2 times minus x squared plus c3 times 1 plus x, I need to set that equal to x squared plus 2x plus 3. We have a polynomial on the left and a polynomial on the right. Two polynomials equal each other if and only if corresponding coefficients are all equal. We can rewrite the polynomial on the left as c1 minus c2 times x squared. There are only two x squared terms. One of them has a coefficient of c1. The other one has a coefficient of minus c2. The only x term is c3 times x, and then the constant terms. We have c1 and c2 and c3. We want this to be equal to the polynomial on the right-hand side, x squared plus 2x plus 3. Polynomials equal each other if and only if corresponding coefficients are equal. This gives us c1 minus c2 equals 1, the coefficient of x squared on the right-hand side. c3 equals 2, and c1 plus c2 plus c3 equals 3. We find that the equality of these two polynomials is equivalent to the solution to a system of equations. Let's write this as an augmented array. We'll have 1, -1, 0, and then 1, 0, 0, 1, and then 2, 1, 1, 1, and then 3. My calculator gives me the reduced row echelon form of 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 2. You might have seen this to begin with. 1 times the polynomial 1 plus x squared plus 0 times the polynomial 1 minus x squared plus 2 times the polynomial 1 plus x gives us x squared plus 2x, and 1 plus 2 makes 3. Mn is the set of all m by n matrices. Here we'll assume that the entries are real, though in some courses the entries are allowed to be complex. As another bit of notation, P sub n is the set of all polynomials of degree n or less. So for example, M22 is the set of all things of the form A, B, C, such that A, B, C, and D are real numbers. Also, for example, P2 is the set of all ax squared plus bx plus c such that a, b, and c are elements of the set of real numbers. As an example, can we write A, which is the matrix 0, -1, 0, as a linear combination of the matrices B equals 1, 1, 0, 0. C is the matrix 1, 1, 1, 0. And D is the matrix 0, 1, 1, 1. You can see we're asking, are there constants C1 times 1, 0, 0, 1 plus C2 times 1, 1, 1, 0 plus C3 times 0, 1, 1, 1. That gives us 0, minus 1, 1, 0. Combining the matrices on the left, we'll have C1 plus C2, and then C2 plus C3, C2 plus C3, and then finally C1 plus C3. We want that to be equal to 0, negative 1, 1, 0. Do you see a problem? We end up with a system of equations. C1 plus C2 equals 0. C2 plus C3 equals minus 1. C2 plus C3 equals positive 1, and C1 plus C3 equals 0. These middle two equations are a contradiction. You can't have something equal to negative 1 and at the same time equal to positive 1. We see that these equations are inconsistent, which means there is no solution. That means our matrix 0, negative 1, 1, 0 cannot be expressed as a linear combination of the other three matrices. In our next example, we're going to show that if the set S consists of x1, x2 through x sub k, if these are solutions to the matrix equation AX 0, then any linear combination of elements of S is also a solution. Note that this as a linear system is a homogeneous linear system. What we're saying is any linear combination of homogeneous solutions to a linear system will also be a homogeneous solution. To prove this, we'll take A times an arbitrary linear combination, C1x1, C2x2 to ckxk. Using the properties of matrix multiplication, we can rewrite this by using the distributive law and the fact that scalars commute with everything as C1 AX1 plus C2 AX2 plus CK AXK. In the hypothesis of this problem, C1 through CK were homogeneous solutions. That means that A times x1 is the zero vector, and A times x2 is also the zero vector, and on down the line. When you rescale the zero vector, you get the zero vector, and when you add the zero vector to something, you get the other thing. So the total is going to be 0, and that completes the proof that linear combinations of homogeneous solutions are homogeneous solutions. I want to look once again at a system AX equals B. Let's start with a particular case. Let's suppose A is 2 by 2, and we have A, B, C, D. Let's suppose x has coordinates x and y. And let's suppose the vector b has coordinates, let's say, beta 1 and beta 2. I didn't want to use b again. Then what we get is ax plus by, cx plus dy equals beta 1, beta 2. The left-hand side can be re-expressed as x times ac plus y times bd. If we can express the matrix A as columns A1, A2 times xy, what we get when we multiply A1, A2 times y is x times A1 plus y times A2. What we end up with is a linear combination of the columns of the matrix A. That's true more generally. What we have is that if A is in AMN, so that it is an M by N matrix, and X is in Rn, we may write A as columns A1 through AN, and X as X1 through Xn. Then A times X will be X1A1 plus X2A2 plus XNAN. We can decompose this matrix product as a linear combination of the columns of the matrix A. We know that A equals B is consistent if and only if this has a solution X. What does that mean? If it has a solution, then X1A1 plus X2A2 through XNAN will be equal to the vector B. That means B is expressible as a linear combination of the columns of A. We have the following theorem. AX equals B is consistent if and only if B may be expressed as a linear combination of the columns of the matrix A. I want you to see something else. Suppose A is the matrix Aij and B is the matrix Bij. Let's look at A times B. By definition, that's the sum, as k goes from 1 to n, of Aik, B, K, J. Let's think about that. Note that if J is equal to 1, we get the first column of the product. That's going to be in the first column, the sum, as k goes from 1 to n, of Aik, B, K1, and then the sum, as k goes from 1 to n, of Aik, B, K2, and so on. BK1 consists of the first column of the matrix B. BK2 is the second column of the matrix B. What we're getting here is A, B1, A, B2, through A, be, well, I haven't decided how big this matrix is. Let's call it P. We'll assume that this is n by P, and this is m by n, so that the product is defined. And this is true where we're assuming that B is the matrix B1 through BP. In other words, when you multiply one matrix times another, what you do is take the matrix on the left and multiply that onto each of the columns of the matrix on the right. We're not trying to do anything very complicated here. What we're trying to do right now is give you the vocabulary that you will need for the rest of the course.